Thank you, Wayne, for this nice introduction. And today I'm going to talk about our work developing new secondary organic aerosol treatments within the E3SM model. I want to acknowledge all my co-authors. This work was recently published in Journal for Advances in Modeling Earth Systems. I also want to acknowledge the US DOE E3SM Atmospheric Physics NGD and also my DOE Early Career Award. So beginning, I just want to introduce quickly what are actually secondary organic aerosols. So in this figure here, you would see that all these sources like sources from either industry or vehicles or plants even, they emit a lot of organic gases in the atmosphere, and these gases react to atmospheric chemistry in the atmosphere, and they are converted to thousands and thousands of fine particles. A key distinguishing factor between secondary organic aerosols and primary organic aerosol is that primary POA or primary organic aerosol is directly emitted. So we know them as things like soot emissions, for example. But secondary organic aerosols start their life cycle as gases. When they are emitted, they are gases, and due to atmospheric chemistry, they either grow the existing particles as they condense on them. So that's what like when you have nucleation of particles, the condensation of organic gases on them grows them to sizes which are relevant to CCN, and then interacts with clouds and radiation. So in that sense, they are really important, and they also come from a variety of sources, like I mentioned. So in that sense, secondary organic aerosol is ubiquitous in the atmosphere. But more importantly, it also, all these emissions of gases from either industries or vehicles or even plants, they are all connected because they interact in the atmosphere with atmospheric chemistry, and then a lot of these SOA particles are created. And when we think about a particle like sulfate or black carbon, it's usually one component. But when we think about SOA, it is a class of thousands of organic compounds. It's not just one chemical component. So in that way, there is a tremendous complexity in secondary organic aerosol formation and knowing its processes and lifetime in the atmosphere. So these are measurements, like this is a classic figure from a science paper from Jimenez et al. And these are aerosol mass spectrometer measurements around the world, which is one of the key instruments which has been instrumental in quantifying and measuring organic aerosols in the atmosphere. So here sulfate is shown in red, as you can see, and the organic aerosols are shown in green. And one thing to note here is that even in many places of the world, especially in the northern hemisphere, SOA concentrations are either similar to or greater than sulfate. And so that has huge implications, because if in climate models and other studies, if we assume that the aerosol is made of just sulfate, it would not be estimating the aerosol cloud interactions correctly, because secondary organic aerosols or organic aerosols have a range of volatilities, hygroscopicities. Their hygroscopicity are often much smaller than sulfate, like factor of 5 smaller than sulfate. But then also, as the SOA particles age in the atmosphere, their O2C ratios and hygroscopicity can increase. So this is I'm showing the IPCC radiative forcing bar chart here, which a lot of us are already familiar with. And here, like, we have warming due to greenhouse gases, but then there is cooling due to things like sulfate, warming due to black carbon on snow and also in the atmosphere. But the key point which I want to draw your attention to is organic carbon is also represented here. But this organic carbon is only the primary organic carbon. Its radiative forcing is minus 0.3 watt per meter square. But SOA or secondary organic carbon, organic aerosols were not even included in this IPCC bar chart. And this is a quote from the IPCC fifth assessment, that there is tremendous complexity and uncertainty in the processes involved in SOA formation. So SOA was not included on this bar chart. So in addition to so in this talk, I'm going to show some of our work in the E3SM model, what it means for the direct radiative forcing. But then even the interaction of SOA with clouds can be a key uncertain component, and that could change the global cloud forcing by 20% with large regional variations. And that has to do with the understanding of SOA processes and how well they are represented in the models. So just to give a perspective, we wrote a review paper in the Reviews of Geophysics in 2017. And what this shows is that you have we cannot think of natural emissions and anthropogenic emissions as completely decoupled from each other, especially when it comes to SOA formation, because the emissions from biogenic sources like isoprene or monoterpene, these gases, they interact with anthropogenic VOCs in the presence of sulfate and NOx and other organic molecules. So there is this understanding the interactions between biogenic emissions and anthropogenic sources has been one of the key questions in atmospheric chemistry and science for decades. And what it really means is that it's the interactions which we really want to understand, because then that changes the phase state of SOA. So SOA can exist as a liquid in some portions of the atmosphere, but also as a semi-solid and solid, which has implications for whether it acts as a CCN or ice nuclei in the atmosphere. And then it has a range of volatility distributions. And so based on these properties, it can affect new particle formation, the growth and evaporation kinetics, heterogeneous and multi-phase chemistry, which affects the lifetime CCN number, the hygroscopicity of particles, and ultimately it interacts with aerosol, with clouds and radiation, and then feeds back into biogenic emissions themselves. So the main thing, the key point here is that in this review article, we really went through and looked at that time what was known about some of the key uncertain processes of SOA, and we have made a lot of advancements with measurements in the last decade or so, both from field measurements, also laboratory measurements with much more advanced instrumentation. And so there is a continuous need to take these measurements and build and include SOA processes in the models, especially related to anthropogenic biogenic interactions, because a lot of the not just regional models, but a lot of the global Earth system models do not include these processes, and this could bias their estimates of radiative forcing between present day and pre-industrial. So I am going to touch on some of the key chemical processes which we considered in our model development. Certainly there is a lot more to go, but these are some of the key ones. So one of the key ideas is that the chemical oxidation reactions can be both sources and sinks of SOA. So you can think of a long organic hydrocarbon species when it reacts with OH groups, for example, in the atmosphere. We are adding functional groups to the carbon chain, so the molecule becomes more functionalized, heavier, and its volatility can decrease. And when the volatility decreases, then that molecule which was in the gas phase can much more easily condense to the particle phase. So this is functionalization can act as a key chemical source of SOA. But in the same time, there are some other reactions with the same oxidants which can break the carbon chain here. So I can see the carbon chain breaking. You get two different molecules which are much more smaller. And so because they are smaller molecules, the volatility increases. And if the volatility increases, that means that the molecule has a more tendency to stay in the gas phase. And that acts like a sink of SOA. And so just to give a perspective of how real the functionalization and fragmentation reactions are, these are measurements from Alan Goldstein's group that was published in PNAS a few years ago. This was done with some of the state-of-the-art instrumentations in the field, so the chemical ionization mass spectrometer and the GC instrument. And you can see that monoterpenes, like with the carbon number of 10, start out in the atmosphere, but as they are aging, you get a lot of functional groups. You are adding functional groups to the carbon chain, but at the same time, you are fragmenting the molecules and you are creating a bunch of fragmented products. So you can see it starts as C10, carbon number 10, but you see a lot of lower carbon number compounds also forming. So just to give a perspective that based on more advanced instruments now, we can see that these effects of functionalization and fragmentation are actually happening in the field. The challenge is how do you parameterize that for a climate model? Because there are thousands and thousands of these species, and it's not feasible to represent all this chemistry in a model for what we know. But we still want to do a good job of representing some of these key processes which affect SOA budgets, loadings, and lifetimes in the atmosphere. So another important experimental finding is photolysis. So these are measurements being shown in the PNNL smog chamber, environmental smog chamber here, where isoprene SOA was generated and then exposed to UV light. And what we found, what this study found, this is from John Schilling and Maria Zawodowicz, was as the UV light is hitting these SOA particles, within 10 to 12 hours, almost 80% of it is gone, because the multifunctional species in the within the SOA particle, when they were exposed to UV light, they reacted away and evaporated to the gas phase. So this is another process which is really important to be considered in climate models. So just now, I want to talk about what we did. So we have the new model developments which we implemented in E3SM. They parameterize multi-generational chemistry of thousands of organic compounds, as I mentioned. So it's not feasible to represent each and every of those thousands of compounds, but we use a volatility basis set approach where it lumps these compounds into fixed volatility intervals, like decadal intervals. So this is what it is shown. It ranges from most non-volatile species to the most volatile species, but you represent this range by these fixed decadal intervals. And so we consider the precursors from both biogenic emissions, from biomass burning emissions, and energy-related emissions. And as I mentioned, we include fragmentation reactions in addition to functionalization. And then we also include the particle phase oligomerization and photolysis of SOA. So a lot of the climate models don't have this complexity of these processes, which are observed from field experiments and lab experiments. And so what they would do is they would change the spatial distributions, the vertical distributions, and lifetimes of SOA. And by doing that, they affect their interaction with clouds and radiative forcing. So the other challenge we had was, okay, we managed to lump it into some volatility bins, but still each volatility bin will have to be represented by several particle phase species. For example, if we have MAM4, we'll have 4 modes to represent each species, and that still increases the number of tracers we need to advect in the model. So we were also dealing with this challenge of how to keep the complexity, how to keep it computationally efficient, but still represent this complexity of SOA formation. So we came up with this algorithm where we added the 8 gas phase species, so which represents the different volatility intervals, like I showed to you before. And then in the gas phase, we have functionalization and fragmentation. And then within the code, we add local tracers to calculate the gas particles partitioning dynamically between the semi-volatile gases and particle phase species. So we have a lot of local tracers now in the code, but then in the end of each time step, once we calculate the partitioning to all the SOA particle species, we lump them together as a single species, which is assumed to form non-volatile oligomers within the particle. And so that reduces, so in that sense, we only have to advect a single SOA species in each mode. So we reduce the number of transported particle phase species. The other simplification we did was like all SOA sources from biogenic, biomass burning, fossil fuel related are lumped with each other. So that resulted in considerable computational savings compared to some of the more complex treatments we had in CESM before. Okay, so now I'm going to show you some more results about the treatment itself. So this is on the left, you see the default treatment where we don't consider photolysis of the particles. We still have functionalization and fragmentation. And you see the hotspots of SOA formation here. over biomass burning regions in Africa, for example. You see hotspots over East Asia, over the South America, and you also see SOA formation here in North America. And then in another simulation, we have photolysis on. So now these particles can get lost by photolysis reactions, and you see a substantial decrease in SOA. And the decrease is maybe 30 to 50% over the source regions, but really over the remote oceanic and high altitude downwind regions, you see much stronger decreases by 80 to 90%. And this is really important. But the key question here is that which of these treatments are actually more consistent with measurements. And so we went to look for aircraft measurements, which have sampled the whole atmospheric vertical column in many locations. So we started with the ATOM 2016 aircraft measurements. Here we are showing evaluation it goes all the way from 0 to 12 kilometer altitudes. This is the equatorial ocean, North America, and this is Southern Ocean. So the advantage of ATOM 2016 was it also sampled a lot of regions over the Southern Ocean. So here we are seeing that in the dark blue, when we don't include photolysis, we can substantially overestimate SOA over some of these remote oceanic regions. Whereas once we include the photolysis, this is seen by the cyan lines, it actually agrees much better. So the measurements are in black here, and the gray shading is the variability of the measurements, and the model predictions are shown by different colors. But as you can see, without photolysis, we overestimate SOA in the upper troposphere. Once we include photolysis, we start seeing a much better agreement, both near the surface and high altitudes. And so the key here is that at high altitudes, when we go above 5 kilometers, the wet removal sink is not efficient. So if we have a strong source of SOA near the surface, which can be carried by convective by convection to high altitudes, we also needed a strong sink of SOA, especially over the Southern Ocean in this region, to explain measurements. And we can clearly see that at high altitude locations, the SOA loadings are reduced by 70 to 90% when photolysis is included. So that plot was for SOA loadings, but then what does it do to CCN? And here again we show that compared to when we don't have photolysis, when we turn photolysis on in the model, the CCN decreases by about 10 to 30% near the surface, but 50 to 70% at high altitudes. So the other thing is, like, we can also validate our model predictions with satellite observations, especially with, for example, when we look at biomass burning regions of Africa, where it is dominated by organic aerosols, and we look at the source evolution from satellites. So if we have a weak chemical source of SOA, we cannot explain the strong formation near the source region. If we have a strong source of SOA, we get too much SOA everywhere. So we found that including both strong chemical source and sink of SOA was needed to explain MODIS observations. And we clearly see here, when we look at absolute AOD with a strong chemical source in the blue, we make too much SOA at all regions. When we have a weaker chemical source, then absolute AOD looks fine. But if we take the ratio of what is in the outflow to inflow, we get higher ratios with a weaker source. So in this case, again, when we have both strong source and sink, we get much better agreement, both in terms of absolute AOD and the evolution of AOD downwind the source region. So the simulated, coming back to the direct radiative forcing, the IPCC radiative forcing for primary organic carbon was -0.3, but it did not include SOA. So if we just look at present day, like using the radiation diagnostics with and without SOA, we get the direct radiative forcing of -0.67 watt per meter square. It's obviously much higher over the source regions. But if we take the difference between present day and pre-industrial, we get, and with photolysis on, we get -0.1. But when we don't have photolysis, we get -0.4. So the key idea is that the photolysis decreases the direct radiative forcing of SOA by a factor of 4. So that really tells the fact that including the processes, the right processes, not just sources, but the sinks of SOA are really important to get a good handle of the radiative forcing. So just some key takeaways that we developed a computationally efficient framework. And this framework, because it explicitly links to emissions from anthropogenic sources, but then also land use changes. Because another thing we found is that due to land use changes, the biogenic emissions have decreased since pre-industrial times. That has strong implications for SOA formation and its radiative forcing. So our framework can be used to explicitly couple with these processes, energy and land use changes, and could answer questions about how these changes in the future could impact aerosol cloud radiation interactions. And we also found that measurements, we have to use vertical profile measurements to constrain SOA formation. A lot of the evaluation is just with surface, but the vertical profiles are really important. We can use satellite measurements, and then ultimately accurately representing these key SOA processes in global models is absolutely essential for understanding their interactions with clouds and radiative forcing. And then just wanted to say that currently, as a part of NGD atmospheric physics, we are coupling our new SOA treatments to the E3SM mosaic code that includes nitrate in addition to sulfate. And I just presented some more thoughts about other potential developments which would be important depending on support. So one thing is that including the treatment of phase state of SOA, because the SOA does not stay as a liquid form throughout the atmosphere. It varies between liquid, solid, and glassy. Especially at high altitudes, it would be more in the solid and glassy phase, and that has implications for things like ice nucleation. So phase state affects both SOA formation and cloud microphysical properties that's not included in current models. The other thing is that really representing the interactions between anthropogenic sulfate and SOA chemistry is important for aqueous aerosols and clouds. So I'm doing this some of this as a part of my DOE early career work in WorkChem model, but then taking the insights which we can gain from other measurements and modeling studies to E3SM will be important. And we so far we have treated SOA as mostly scattering, but also including its absorbing properties and evaluating their role is going to be important. Thank you.